Hello there, and welcome to the Sleepy Library. Tonight, we are drifting into the magnificent realm of our home galaxy, the Milky Way. A vast spiral of stars, dust, and mysteries that has turned slowly through space for over 13 billion years. This is not just a journey through our cosmic neighborhood. It is a journey through wonder, into the hidden architecture of the universe itself. The things we will discover are not only strange, but beautifully real. These revelations might challenge what we think we know about our place in the cosmos, or what a galaxy even is. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the night sink around you and allow your mind to settle. Let's begin. The Milky Way is a barred spiral galaxy. When we look up at the night sky on a clear evening, away from city lights, we see a pale band of light stretching across the darkness like spilled milk. That luminous river gave our galaxy its name. But from our vantage point inside the galaxy, we cannot see its true shape. We are embedded within it, like a person standing in a forest trying to understand the pattern of the trees. If we could somehow travel far beyond our galaxy and look back, we would see something magnificent. A great pinwheel of stars, roughly 100,000 light-years across, with elegant spiral arms curving outward from a bright central bulge. The disk itself is remarkably flat, only about 1,000 light-years thick at the spiral arms, though it thickens near the center, where ancient stars cluster in a peanut-shaped bulge. Recent observations have revealed that at the heart of this structure lies a bar, a thick bridge of stars extending across the central regions, rotating slowly and shepherding gas inward to feed new generations of stars. The Milky Way contains between 200 billion and 400 billion stars. Imagine trying to count every star in our galaxy. If you counted one star each second, never stopping to rest, it would take you more than 6,000 years just to reach 200 billion. And still, you would only be counting the visible stars, the ones we can detect with our instruments. There may be countless more, dim red dwarfs and brown dwarfs that glow so faintly they remain hidden from our surveys. Each of these stars is a sun, perhaps with its own family of planets, moons, and mysteries. Some are massive blue giants burning through their fuel in mere millions of years. Others are tiny red dwarfs that will shine for trillions of years, long after our own sun has faded. The diversity is staggering. Young stars blaze with fierce heat in stellar nurseries. Old stars drift through the halo like ancient wanderers. Binary pairs orbit each other in gravitational dances. Some stars race through space at incredible speeds, while others move with serene patience. And at the center of it all, billions upon billions of stars swirl in their orbits, each following the invisible pull of gravity across billions of years. Our solar system orbits the center of the Milky Way at over 828,000 kilometers per hour. That is more than 230 kilometers every single second. And yet, despite this tremendous speed, it takes approximately 225 million years to complete just one orbit around the galaxy. Astronomers call this vast circuit a galactic year. In Earth time, our solar system has only traveled around the Milky Way about 20 times since it formed 4.6 billion years ago. Think about what that means. When dinosaurs first walked the Earth, we were in a completely different part of the galaxy. The stars visible in our night sky were different stars. The constellations that ancient humans recognized and named did not exist in the same patterns. Everything is in motion, quietly, slowly, endlessly. Even as you rest tonight, the Earth turns, the Moon circles, and the entire solar system sweeps forward through space on its long journey around the galactic center. At the very heart of the Milky Way lies an enormous black hole. It is called Sagittarius A*, named for its location in the constellation Sagittarius. This supermassive black hole contains the mass of more than 4 million suns, yet it occupies a space smaller than the orbit of Mercury. Its gravity is so intense that nothing can escape once it crosses the event horizon, not even light itself. We cannot see the black hole directly, but we have watched stars whip around it at tremendous speeds, tracing invisible loops through the void. One star, known simply as S2, completes its orbit around Sagittarius A* in just 16 years, racing through space at nearly 5,000 kilometers per second at its closest approach. In 2022, astronomers captured the first direct image of the environment around Sagittarius A*, using a network of radio telescopes spanning the entire Earth. The image shows a glowing ring of superheated gas spiraling around a dark central shadow, the boundary beyond which no light can escape. Recent observations in polarized light have revealed strong, organized magnetic fields spiraling from the edge of the black hole, suggesting that Sagittarius A* may harbor a hidden jet of material shooting outward into space. For now, this monster sleeps quietly, but long ago it may have burned like a quasar, lighting up the galaxy from within. The galaxy is still growing. Although the Milky Way is ancient, it is not finished. Even now, it continues to gather material. Gas flows in from the intergalactic medium, providing fresh fuel for new stars. Small dwarf galaxies drift too close and are captured by our gravity, their stars gradually absorbed into our halo. Streams of dark matter feed the invisible scaffolding that holds everything together. This growth happens not like the growth of a living thing, but like a gravitational structure deepening over time. Some of this accumulation occurs quietly, through clouds of infalling gas. Other times, it comes with disruption as satellite galaxies are torn apart and their stars scattered across the sky like cosmic confetti. The galaxy you live in today is not the same one that existed when dinosaurs roamed the Earth. And the galaxy your distant descendants may know could be larger still, stitched together from the ruins of 1,000 smaller worlds that wandered too close to resist our pull. The Milky Way has already collided with other galaxies, and it will again. Our galaxy may feel like a stable home, but it is built from the wreckage of others. Over billions of years, the Milky Way has absorbed smaller galaxies, drawing them in, unraveling them, and scattering their stars into long tidal streams that wrap around the disk like ribbons. One such galaxy, the Sagittarius Dwarf Elliptical, is being pulled apart right now. Astronomers have traced its remains in stellar streams that loop around our galaxy, fossil evidence of an ancient collision still in progress. Far off in the night sky, visible as a faint smudge to observers in the northern hemisphere, the Andromeda Galaxy drifts slowly closer. It contains roughly 1 trillion stars, making it even larger than the Milky Way, though recent measurements suggest our galaxy may be more massive due to its extensive dark matter halo. In about 4.5 billion years, the two great spirals will merge in a cosmic collision. Stars will almost never hit each other because space is so vast. But the galaxy's shapes will change forever, folding and stretching into new forms. The merger will likely create an enormous elliptical galaxy, a glowing sphere of stars where once two spirals danced. Even galaxies are not eternal. They evolve, collide, and begin again. Some stars in the Milky Way are older than the Milky Way itself. Not every star in our galaxy was born here. Some halo stars, ancient, metal-poor, and wandering in long, tilted orbits high above the galactic plane, appear to have formed even before the Milky Way had fully taken shape. Astronomers believe these stars may have originated in smaller, primordial galaxies that merged with our own billions of years ago. Their chemical fingerprints show almost no heavy elements like iron or carbon, suggesting they were born shortly after the Big Bang, when the universe contained only hydrogen, helium, and traces of lithium. These ancient stars move slowly through the outer reaches of our galaxy, like elder spirits from a time before spirals, before order. In their dim light, we glimpse a universe that was younger, wilder, and still learning to become what it is. They are time capsules, preserving the conditions of an epoch long forgotten, when the first galaxies were just beginning to assemble from primordial clouds. Dark matter holds the Milky Way together. By all logic, based on what we can measure and see, the Milky Way should not exist. The stars, dust, and gas we observe do not contain enough mass to generate the gravitational force needed to hold the galaxy together. Stars at the outer edges are spinning too fast. They should be flung into space, scattered like leaves in a storm. And yet they remain, bound in stable orbits. The answer lies in something we cannot see directly: dark matter. This mysterious substance does not shine, reflect light, or emit any radiation we can detect. But it exerts gravity, and there is so much of it that it outweighs all the visible matter in the galaxy many times over. Current estimates suggest dark matter makes up roughly 85% of the Milky Way's total mass. We know it exists because of its gravitational effects on visible matter. We can observe how stars and gas move, how light bends around massive objects, and how galaxies rotate. All of these phenomena require far more mass than we can see. Dark matter is the invisible scaffolding that holds everything in place, extending far beyond the visible disk, in an enormous spherical halo that may stretch hundreds of thousands of light-years into space. The Milky Way's disk is warped. Our galaxy does not lie perfectly flat like a dinner plate. Its disk bends upward on one side and downward on the other, forming a graceful wave across vast distances. This subtle warp was invisible to us until radio telescopes mapped the neutral hydrogen gas that extends far beyond the visible starlight. The distortion may be caused by the gravitational pull of satellite galaxies tugging gently on the Milky Way's edges, or by clumps of dark matter bending the structure from below. Like ripples in a great spinning sheet, the warp reveals that even galaxies are never fully still. Over billions of years, they bend, flex, and change form in response to invisible forces. From a distance, if we could see it, the Milky Way might look like it is dancing slowly through space, its disk undulating like a flag in a gentle cosmic breeze. We live in a minor spur between major spiral arms. Our solar system does not lie in one of the Milky Way's grand spiral arms. Instead, we occupy a small structure called the Orion Spur, sometimes called the Orion Arm. A relatively quiet lane of stars nestled between the larger Sagittarius and Perseus arms. It is not especially dense, nor especially active, but that may be one reason we are here. In the calm between galactic highways, massive supernovae are rarer, and radiation storms less frequent. This quiet corner may have given life on Earth the time and stability it needed to emerge and evolve over billions of years. From our perspective, looking inward toward the galactic center or outward toward the periphery, we see only a fraction of the galaxy's true grandeur. We are like passengers on a ship who cannot see the ocean's full expanse. But that limited view also provides a kind of safety. Orbit at a comfortable distance from the violent core and the sparse outer regions, in a zone where conditions are just right for worlds like ours to exist. The center of the galaxy is dominated by old red stars. Surrounding the supermassive black hole at the heart of the Milky Way is a dense region called the galactic bulge. This peanut-shaped structure measures approximately 10,000 light-years across and contains about 10 billion stars. Most of these stars are ancient red giants that formed in the early stages of the galaxy's evolution, more than 10 billion years ago. They glow with a warm reddish light, very different from the hot blue stars found in the spiral arms. The bulge is a crowded place. Stars there are packed much more tightly than in our neighborhood. If Earth orbited a star in the galactic bulge, our night sky would be ablaze with thousands of brilliant stars, so close and bright that darkness would never truly fall. But with that beauty would come danger. The intense radiation from nearby supernova and the chaotic gravitational environment might make stable planetary systems rare. The bulge also rotates as a whole, like a solid structure, which creates the bar at the galaxy's center. This bar funnels gas inward, feeding the central black hole and triggering bursts of star formation in the inner regions. Rogue stars are flung from the galactic core. Most stars drift calmly through the galaxy in orderly orbits, but a rare few are flung outward at astonishing speeds, fast enough to escape the Milky Way entirely. These are called hypervelocity stars. Some are the remnants of binary systems disrupted by the supermassive black hole at the center of the galaxy. Picture a pair of stars orbiting each other, drifting too close to Sagittarius A*. The immense tidal forces can rip them apart. One star falls into the black hole and vanishes forever. The other is slingshot outward, hurled into the dark at over 1 million kilometers per hour. These rogue stars travel alone, far from the galactic plane, like glowing comets with no return. They remind us that even in a galaxy bound by gravity, there are moments of violent release, quiet expulsions that send stars flying into the intergalactic void. Some of these stars may eventually escape our galaxy completely and spend eternity drifting through the empty spaces between galaxies, solitary wanderers in an infinite dark. The Milky Way has a vast invisible halo. Beyond the flat spiral disk lies something far more diffuse and mysterious, a spherical halo that surrounds the entire galaxy. This halo contains ancient stars, globular clusters of stars bound tightly together, and enormous amounts of dark matter. Though it is nearly invisible in ordinary light, this halo may hold the majority of the Milky Way's mass. The stars scattered through the halo are spread thin across vast distances, orbiting in long, slow arcs that rarely touch the disk. Many of these stars are incredibly old, formed before the disk itself took shape. They carry chemical signatures of the early universe, with very few heavy elements in their composition. The halo also preserves the remnants of ancient galactic mergers. Long streams and shells of stars, torn from smaller galaxies billions of years ago, still drift through this outer region like cosmic fossils. The halo is the galaxy's outer memory, quiet and dim, but still in motion, still shaping what the Milky Way becomes. It extends so far that its true edge is difficult to define. Where does the Milky Way end and intergalactic space begin? The answer depends on how you measure it. The visible disk may be 100,000 light-years across, but the dark matter halo could extend for hundreds of thousands of light-years, perhaps even approaching 1,000,000 light-years in diameter. The galaxy contains over 150 globular clusters. Globular clusters are among the oldest objects in the Milky Way. These compact spheres contain hundreds of thousands of tightly bound stars, packed into regions only tens of light-years across. They orbit the galactic center in the halo, like moths circling a distant flame. Many of these clusters are incredibly ancient, more than 12 billion years old, meaning they formed when the universe itself was very young. Their stars are metal-poor, meaning they contain very few elements heavier than hydrogen and helium, because they were born before generations of supernovae had enriched the cosmos with carbon, oxygen, iron, and other elements. Globular clusters serve as time capsules, holding clues to how the galaxy formed, what it consumed during its assembly, and what conditions were like in the early universe. These ancient golden spheres drift patiently above and below the galactic plane, glowing softly in the dark. Some orbit in the inner regions, others venture far into the outer halo. Their orbits are often highly elliptical, carrying them on long journeys through the galaxy's gravitational landscape. Studying their motions helps astronomers map the distribution of dark matter and understand the Milky Way's total mass. Star formation is slowing down. Long ago, when the Milky Way was young, it was far more active, bursting with fresh stars born from dense, collapsing clouds of gas. The galaxy blazed with the light of new suns, hot and blue, illuminating vast nebulae. But in recent cosmic epochs, the pace has slowed considerably. Star formation in the Milky Way peaked billions of years ago and has been declining ever since. There is still gas available for making new stars, but much of it is now spread thin, heated by stellar radiation, or locked in stable forms that resist collapse. The galaxy is not done making stars, but it is settling into a quieter phase. Astronomers estimate that the Milky Way currently forms new stars at a rate of about 1 to 2 solar masses per year. That might sound like a lot, but it means it would take hundreds of millions of years to create stars totaling just a fraction of the galaxy's current stellar population. We live in a mature spiral galaxy, glowing gently in its middle age, still forming stars, but no longer in a hurry. This gradual decline in star formation is common among galaxies of the Milky Way's age and type. Eventually, billions of years from now, the gas will be exhausted or expelled, and star formation will cease altogether. The Milky Way and Andromeda are on a collision course. High above the horizon on autumn evenings in the northern hemisphere, the Andromeda galaxy appears as a faint oval smudge to the naked eye, a spiral much like our own, lying over 2 million light-years away. Despite this vast distance, it is moving steadily toward us. Astronomers have measured its motion through space using the Doppler shift of its light. Andromeda is approaching the Milky Way at approximately 120 kilometers per second. That might not sound like much on cosmic scales, but over billions of years, it adds up. In about 4.5 billion years, the two galaxies will collide. The merger will not be violent in the way you might imagine. Stars are spaced too far apart to crash directly. The average distance between stars is measured in light years, while the stars themselves are only a few million kilometers across. The chances of two stars actually colliding during the merger are astronomically small, but the gravitational forces involved will be immense. Both galaxies will warp and stretch, their spiral arms pulled into long tidal tails that curve outward into space. The shapes we recognize will be lost. Over billions of years, as the two galaxies pass through and around each other multiple times, their orbits will decay, and they will eventually settle into a single, larger elliptical galaxy. Astronomers have playfully named this future merger Milk-Ometer or Milk-Drometer. By that time, our Sun will likely have evolved into a red giant, and Earth, if it still exists, will be uninhabitable. But the stars themselves will endure, scattered into new configurations across a transformed cosmic landscape. Some stars orbit the Milky Way in the opposite direction. Most stars in the Milky Way orbit the center in the same general direction, following the overall rotation of the galactic disk. But not all follow this pattern. Some stars, especially those in the outer halo, move in retrograde orbits, circling the galaxy in the opposite direction. These stars likely arrived from elsewhere, born in dwarf galaxies that were later absorbed by the Milky Way. Their reversed motion is a quiet signature of their foreign origin, a kind of cosmic accent that marks them as immigrants. It is as if the galaxy carries old memories in its motion, stories of ancient mergers and cosmic encounters preserved not in light, but in the slow, patient turning of stars against the stream. By studying the orbits of these retrograde stars, astronomers can reconstruct the history of galactic Milky cannibalism, identifying which dwarf galaxies were consumed and when. Each unusual orbit tells a story of disruption and assimilation, a chapter in the long history of how the Milky Way grew. The Milky Way may have consumed dozens of dwarf galaxies. Over billions of years, the Milky Way has not grown alone. It has consumed smaller galaxies, faint dwarf companions that drifted too close and were caught in its gravitational embrace. These smaller galaxies were slowly dismantled, their stars now part of our halo, disk, or stellar streams. Astronomers have identified several of these ancient mergers by analyzing the motion and chemical composition of stars. One especially significant event, known as the Gaia-Enceladus merger, occurred about 10 billion years ago, when a dwarf galaxy with a mass of several billion suns collided with the young Milky Way. This collision may have reshaped the early structure of our galaxy, thickening the disk and scattering stars into the halo. The Milky Way is not a pristine spiral that formed in isolation. It is a composite, built from quiet collisions, stitched together from the remains of many smaller worlds. Each merger adds new stars, new gas, and new complexity to the galactic ecosystem. The process continues today. Right now, as you rest, the Sagittarius dwarf elliptical galaxy is being torn apart by tidal forces, its stars streaming across our sky in long arcs that will eventually blend into the Milky Way's population. The chemical makeup of stars reveals their origin. Every star carries a unique chemical fingerprint, a pattern of elements imprinted at birth from the cloud of gas and dust that collapsed to form it. By studying these signatures through spectroscopy, breaking starlight into its component colors, and analyzing the dark absorption lines created by different elements, astronomers can trace a star's history. Some stars are rich in heavy elements like iron, silicon, and calcium, suggesting they formed in dense, metal-rich regions of the galactic disk, where generations of supernovae had enriched the gas. Others are nearly pure hydrogen and helium, born when the universe was still young and few heavy elements existed. These differences allow scientists to group stars into populations, uncover ancient mergers, and reconstruct the hidden story of the Milky Way's formation and evolution. In this way, chemistry becomes a kind of time machine, letting us read a star's past like lines of ancient poetry written in light. Each element tells part of the story. Carbon and oxygen were forged in the cores of massive stars. Iron and nickel came from supernova explosions. Gold and platinum were created in the collisions of neutron stars. The elements in your own body, the calcium in your bones, the iron in your blood, all were created in stars and scattered into space by cosmic violence, eventually gathering into the cloud that formed our solar system. The sky is full of stellar streams from shredded galaxies. Across the sky, invisible to the naked eye but revealed by careful surveys, thin ribbons of stars stretch in arcs and curves. These are stellar streams, the remnants of smaller galaxies that wandered too close to the Milky Way and were pulled apart by tidal forces. As these doomed galaxies orbit our galactic center, their stars are smeared across space, forming long, delicate trails that trace their former paths. Some streams wrap around the galaxy multiple times, like ghostly halos. Others plunge inward toward the core. These streams are evidence of past collisions, quiet mergers that built the Milky Way over billions of years. The galaxy, like a tree, carries the rings of its past in every thread of light. One of the most prominent streams comes from the Sagittarius dwarf elliptical galaxy, which is currently being consumed. Its stars form a stream that loops entirely around the Milky Way, a cosmic ribbon that marks the path of its destruction. By mapping these streams and measuring the velocities of their stars, astronomers can reconstruct the orbits of the galaxies that created them and learn about the distribution of dark matter in our galactic halo. You can only see about 0.00003% of the Milky Way with the naked eye. Under a perfectly clear, dark sky, far from cities and artificial lights, you might see a few thousand stars scattered across the heavens. To the human eye, that seems like an ocean of light, a magnificent display of cosmic splendor. But it is barely a droplet. The Milky Way contains over 200 billion stars, possibly as many as 400 billion. Most are hidden from our view. Some lie behind thick curtains of interstellar dust. Others are simply too faint or too distant for our eyes to detect. The pale streak of the Milky Way that arches across the night sky on moonless nights is just the innermost whisper of the whole, the densest part of the galactic plane, where stars cluster most thickly. We live surrounded by a colossal river of starlight, and yet almost all of it remains invisible to us, too vast to grasp from within. If we could see every star, the night sky would be ablaze with light, hardly dark at all. The darkness we experience is a result of our limited vision and the sheer scale of the galaxy. Stars orbit the galaxy at different speeds. Unlike planets in a solar system, which follow neat, predictable orbits determined by the sun's gravity, stars in the Milky Way move with more complexity. Some race ahead in the inner regions, completing orbits relatively quickly. Others drift slowly along the outskirts, taking hundreds of millions of years to circle the galactic center once. This difference in orbital speeds is one reason spiral arms form. The arms are not solid structures composed of the same stars rotating together. Instead, they are density waves, patterns like slow traffic jams, where stars and gas temporarily crowd together. As these density waves pass through them, they compress clouds of gas and trigger the birth of new stars. Young, hot blue stars light up the arms in brilliant spirals of blue and white light. Our own sun is part of this swirl, moving in and out of these patterns across time. The galaxy is not a rigid clock. It is a fluid, ever-changing current, and we are drifting in it, carried along by gravity's invisible tide. The galaxy's rotation defies simple physics. According to Newtonian mechanics, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system move more leisurely around the Sun. The gravitational pull weakens with distance, so objects farther out should take longer to complete their orbits. But observations of the Milky Way reveal something unexpected. Stars in the outer regions orbit almost as quickly as those closer to the center. Their velocities remain relatively constant, even at great distances from the galactic core. This flat rotation curve, as astronomers call it, cannot be explained by the visible matter alone. The reason, scientists believe, is dark matter. An invisible, unknown form of mass surrounds the galaxy in a vast halo, providing the extra gravitational force needed to keep the outer stars moving quickly. Without dark matter, the galaxy would fly apart, stars escaping into the void. With it, the rotation makes sense. The Milky Way turns like a more solid wheel than it should, held together by something unseen. This discovery, first made in the 1970s, was one of the earliest pieces of evidence for dark matter's existence, and remains one of the strongest arguments that something beyond ordinary matter shapes the universe. The Milky Way has enormous molecular clouds. Scattered throughout the galactic disk are vast, dark clouds of cold gas, the raw material from which stars are born. These molecular clouds, composed mostly of molecular hydrogen, along with traces of carbon monoxide, ammonia, and other compounds, can span hundreds of light-years across. Within their cold, dense interiors, temperatures drop to just a few degrees above absolute zero. Gravity begins to gather material in certain regions, forming clumps that collapse inward to create new stars and planetary systems. Some of these clouds are so large and so cold that they absorb visible light entirely, appearing as black patches against the starry sky, like holes in the fabric of space. They are the galaxy's wombs, quiet, hidden places where the future begins in silence, tucked within curtains of shadow and frozen gas. These clouds are not uniform. They have complex internal structures, with filaments, dense cores, and regions where star formation has already begun. When massive young stars ignite within a molecular cloud, their intense radiation and stellar winds can blow away the surrounding gas, revealing the newborn stars and creating beautiful nebulae that glow with the light of ionized hydrogen. Supernovae stir the galaxy like cosmic storms. When massive stars reach the end of their lives, they explode in cataclysmic supernovae, events so powerful they can briefly outshine entire galaxies. These explosions do not just mark the death of a star, they are moments of creation and renewal. The shock waves from supernovae ripple through the interstellar medium, the thin gas that fills the space between stars, compressing nearby clouds and triggering new waves of star formation. Material ejected from the dying star, enriched with heavy elements forged in its core and during the explosion itself, mixes with the surrounding gas. This enrichment provides the raw ingredients for future generations of stars and planets. Elements like iron, gold, carbon, and oxygen are scattered into space, eventually incorporated into new stellar systems. In this way, supernovae act like storms within the galactic ecosystem, stirring, fertilizing, and reshaping everything around them. They are the galaxy's moments of chaos, destructive and radiant, but also necessary for the ongoing cycle of stellar birth and death. Without supernovae, the universe would be composed almost entirely of hydrogen and helium. Rocky planets like Earth could not exist. Life itself depends on the heavy elements created and distributed by these stellar explosions. Dust hides vast regions of star formation. The Milky Way is full of light we cannot see with ordinary telescopes. Interstellar dust, made of microscopic grains of carbon, silicon, and ice, weaves through the galaxy in clouds and tendrils, filling the space between stars. In visible light, this dust obscures vast regions, blotting out stars and entire nebulae like a cosmic fog. But behind this veil, star formation continues unabated. Infrared telescopes can peer through the dust, revealing glittering nurseries filled with newborn suns, glowing warmly in wavelengths invisible to our eyes. What looks like darkness in optical images is often a cradle of creation. The dust, though it hides, is part of the process. It absorbs starlight and re-emits it as infrared radiation. It helps gas clouds cool, allowing them to collapse under their own gravity. It shields delicate stages of stellar birth from disruptive radiation. What seems like emptiness is often the beginning of something bright. Some of the most famous star-forming regions in the Milky Way, such as the Orion Molecular Cloud Complex and the Eagle Nebula, are dense with dust. Only by observing in infrared and radio wavelengths can we see the full picture of what is happening within these stellar nurseries. There are starless gas clouds drifting through the galaxy. Not every cloud of gas becomes a star. Across the Milky Way, astronomers have found massive, cold clouds that seem destined for collapse, yet remain dark and dormant. Some are too diffuse to gather enough material. Others may be stabilized by magnetic fields threading through them, providing support against gravitational collapse. Internal turbulence, chaotic motion of gas within the cloud, can also prevent star formation by dispersing material before it can accumulate into dense cores. These starless clouds float through the galaxy like silent possibilities, rich in molecular hydrogen, but untouched by the fires of fusion. They may one day ignite if disturbed by a passing shockwave or the influence of a nearby supernova. Or they may drift until torn apart by external forces, their gas recycled into other regions of the interstellar medium. In these clouds, the galaxy holds its breath, waiting, perhaps for the right nudge to spark something new. Their existence reminds us that star formation is not inevitable. It requires a delicate balance of conditions, and even clouds with all the right ingredients may remain dormant for millions of years. The Milky Way recycles matter across generations of stars. Stars are not permanent fixtures in the sky. They live, burn through their nuclear fuel, and eventually die, returning their material to the galaxy. When massive stars explode as supernovae, they scatter their enriched contents into space. When smaller stars like our Sun die more gently, they shed their outer layers in beautiful planetary nebulae, puffing shells of glowing gas into the interstellar medium. This material, now enriched with carbon, nitrogen, oxygen, and heavier elements, joins the vast clouds of gas and dust that fill the galaxy. Over time, gravity pulls these clouds together, and new stars are born from the ashes of the old. Planets form from the same material. Even life arises from these recycled elements. Every atom in your body has passed through this cycle. The calcium in your bones was forged in the heart of a massive star. The iron in your blood was created in a supernova explosion. The oxygen you breathe was produced by stellar fusion. You are made of stardust, quite literally, composed of atoms that have traveled across the galaxy and through multiple generations of stars before coming together to form you. The Milky Way is not a static stage, but a great engine of renewal, breathing in time with its stars, making, unmaking, and beginning again in an endless cycle that has continued for billions of years. Metal-poor stars hold clues to the early universe. In astronomy, metals are not just iron or gold. The term refers to any element heavier than helium. The earliest stars in the universe had almost none of these metals, because they formed from primordial gas clouds composed only of hydrogen and helium, the elements created in the Big Bang. As these first stars lived and died, they forged heavier elements in their cores and scattered them through supernovae. Subsequent generations of stars were born from gas enriched with these metals. By studying metal-poor stars in the halo of the Milky Way, astronomers peer into the ancient past. These stars, faint and old, preserve the chemical conditions of a time long gone, an era shortly after the Big Bang, before galaxies had fully failed. Matured and heavy elements were common. Their atmospheres contain less than 1/10,000th the iron found in the Sun. They are fossils made of light, glowing embers from the dawn of time. Each one offers a glimpse into the conditions of the early universe and the processes that led to the formation of the first galaxies. Some of these stars are so old they may have formed within the first billion years after the Big Bang, making them older than most structures in the visible universe. Some stars wander far from where they were born. A star's birthplace does not always define its destiny. Over billions of years, many stars drift away from their natal clouds, pushed by gravitational interactions with other stars, by the slow pull of spiral arms, or by close encounters with massive objects. Some stars are ejected at high speeds, during violent events such as supernova explosions in binary systems, or close passes near the galactic center. Others migrate gradually, their orbits shifting inward or outward as they spiral through the galaxy under the influence of gravitational perturbations. Even our Sun is not where it began. Born in a stellar nursery somewhere in the galaxy, it has since wandered through the disk, drifting from its original location. Tracing the paths of stars reveals a Milky Way that is anything but static. It is a galaxy alive with movement, exchange, and quiet dislocation. The stars we see today are not in their original positions. They have traveled vast distances, some covering thousands of light-years during their lifetimes. Home, for a star, may only be temporary. The dynamic nature of the galaxy ensures that stellar neighborhoods are constantly changing, mixing stars from different regions and different eras. The galaxy's habitable zone may span tens of thousands of light-years. Just as Earth orbits in a Goldilocks zone around the Sun, not too hot nor too cold for liquid water to exist, the Milky Way may have its own galactic habitable zone. This region is thought to lie between the dangerous inner core, full of intense radiation from supernovae, and gravitational chaos near the supermassive black hole, and the sparse, metal-poor outer edges, where the elements necessary for rocky planets and life are scarce. Somewhere in between lies a wide band where conditions are stable, star density is moderate, and elements like carbon, oxygen, nitrogen, and iron are abundant. Our solar system lies within this zone, about halfway out from the center. This fortunate position may have been crucial for the development of life on Earth. Too close to the center, and frequent supernovae or gamma-ray bursts could have sterilized our planet. Too far out, and the lack of heavy elements might have prevented the formation of a rocky planet with a protective atmosphere. The galactic habitable zone is not a fixed boundary, but a dynamic region that changes over time as the galaxy evolves. As star formation slows and older stars die, the zone may shift or expand. Understanding where this zone lies and how it has changed helps astronomers in the search for life beyond Earth, guiding efforts to identify promising regions where habitable planets might exist. The spiral arms are not fixed structures. The Milky Way's spiral arms might seem like permanent features, grand sweeping lanes carved into the galaxy's disk. But they are not made of the same stars rotating together like the blades of a fan. Instead, they are density waves, patterns that ripple slowly through the disk, compressing gas and triggering bursts of star formation as they pass. Individual stars drift into these arms, shine brilliantly for a while, and then drift out again. The spiral structure itself moves at a different speed than the stars, like a traffic jam moving through a highway while individual cars pass in and out. The arms appear bright because they are regions of enhanced star formation. When gas clouds are compressed by the density wave, they collapse and form new stars. The hottest, most massive stars burn blue and white, illuminating the arms with brilliant light. These stars have short lifetimes, only a few million years, so they do not drift far from their birthplaces before exploding as supernovae. This is why the spiral arms remain well-defined and bright. Lower mass stars like our Sun live much longer and have time to drift away from the arms after they form, blending into the general stellar population of the disk. From afar, the spiral pattern looks like form and order, a beautiful cosmic design. From within, it is a pattern of shifting motion, held together by gravity and time, never still, always flowing. The Milky Way hums with invisible cosmic energy. Beyond visible light, the galaxy glows in a spectrum of radiation that our eyes cannot see. Cosmic rays, high-energy particles born in supernova remnants and other violent events, stream through space at nearly the speed of light. They pass through your body every second, mostly without interaction, ghostly messengers from distant explosions. X-rays and gamma rays shimmer from dying stars, neutron stars, and the region around the central black hole. Radio waves drift from vast clouds of hydrogen, from pulsars spinning with clockwork precision, and from the cold breath of molecular gas. These invisible emissions reveal what visible light cannot: the violence, the magnetism, the ancient fires still flickering within the galaxy's bones. When you look up at the night sky, you are seeing only a narrow band of the Milky Way's true output. Beneath the stars, the galaxy hums softly in many frequencies, many colors, a hidden symphony in the dark. This multi-wavelength view has transformed our understanding of the galaxy, revealing processes and structures that remained hidden for centuries. From the coldest molecular clouds emitting in the far infrared, to the hottest accretion disks around black holes glowing in X-rays, each wavelength tells a different part of them. The story. There is a giant gamma-ray bubble above and below the galactic center. Stretching tens of thousands of light-years above and below the central regions of the Milky Way are two vast, ghostly lobes of high-energy light. Known as the Fermi bubbles, named after the Fermi Gamma-ray Space Telescope that discovered them, these enormous structures glow in gamma rays, the most energetic form of light. They extend like twin balloons from the Milky Way's heart, reaching altitudes far above the disk. No one is entirely certain what caused them. They may be the remnants of a long-ago outburst from the central supermassive black hole, Sagittarius A*, during a period when it was actively feeding on large amounts of gas and shining brightly. Alternatively, they could be the result of fierce bursts of star formation that once flared through the core, producing numerous supernovae in rapid succession. Either way, these enormous structures drift silently over the galaxy, invisible to optical telescopes but blazing in gamma rays. They are reminders that the Milky Way has a turbulent past we cannot fully see. Echoes of violence wrapped in high-energy radiation far above the stars we know. The bubbles are roughly symmetrical, suggesting a single, powerful event or process rather than random occurrences. Their edges are sharply defined, which is unusual for diffuse structures in space, and studying them may provide clues to the history of activity at the galactic center. The Milky Way has a bar-shaped center. When astronomers peer toward the galactic core using infrared telescopes that can see through the intervening dust, they observe not a perfect circular bulge, but a thick, elongated bar of stars crossing the middle. This bar is a prominent feature, a kind of glowing bridge made of densely packed stars, extending about 10,000 light-years from end to end. It rotates slowly, completing one turn every few 100 million years, and its gravitational influence is profound. The bar helps shepherd gas inward toward the central regions, funneling material that can feed the supermassive black hole or trigger new episodes of star formation. Bars like this are common in spiral galaxies. Studies suggest that roughly 2/3 of all spiral galaxies have bars at their centers. These bars can form naturally as instabilities develop in a rotating disk of stars. Over time, the gravitational interactions between stars can cause them to drift inward and pile up along a central axis, creating the elongated structure we observe. The Milky Way's bar is not just a shape, it is a dynamic engine, sculpting the galaxy's structure from within, influencing the orbits of stars and the flow of gas across vast regions of the disk. Its presence affects the spiral arms, the distribution of star formation, and even the long-term evolution of the galaxy. It is part of a larger structure called the local group. The Milky Way does not exist in isolation. It belongs to a collection of more than 50 galaxies known as the local group, a small cluster of galaxies drifting together through space, bound by mutual gravity. The two largest members are the Milky Way and Andromeda, each a giant spiral surrounded by its own family of smaller satellite galaxies. The local group spans more than 10 million light-years, a vast expanse, yet it is only a tiny corner of the universe. Scattered around these giants are smaller dwarf galaxies, faint elliptical systems, and irregular galaxies so dim they are barely visible even with powerful telescopes. Many of these dwarfs are composed mostly of dark matter, with only a sparse scattering of visible stars. The local group is not a static arrangement. Its members move and interact, influenced by each other's gravity. Some smaller galaxies orbit the Milky Way like moons, looping through the halo on long elliptical paths. Others are falling inward, slowly being torn apart and absorbed. The gravitational dance of the local group shapes its evolution, and over billions of years, its structure will continue to change. Ultimately, the Milky Way and Andromeda will dominate, merging into a single massive elliptical galaxy, while smaller members either join the merger or are flung into intergalactic space. Galaxies in the local group are gravitationally bound. Despite their vast separations, the galaxies of the local group are not drifting apart in the expansion of the universe. They are gravitationally bound, moving slowly toward one another, or orbiting in complex patterns determined by their combined mass. Gravity holds them in a kind of slow-motion ballet that has unfolded over billions of years. Some of the smallest galaxies orbit the Milky Way like satellites, looping through the halo and gradually losing stars to tidal stripping. Others drift independently, but remain tethered to the group. Over cosmic time, this structure may condense further. Galaxies may merge, fade, or be absorbed. It is not a static arrangement, but a gentle gathering of cosmic islands, a family drawn closer by time, inertia, and the long reach of gravity. The local group provides a unique laboratory for studying galaxy interactions and evolution on relatively small scales. Because these galaxies are nearby, Astronomers can observe individual stars, measure precise distances, and track motions over time in ways impossible for more distant galaxies. The galaxy's disk has a thick and thin component. The Milky Way's disk may look flat from a distance, but up close it reveals layers. The thin disk is where most of the action occurs. It is a dense plain filled with young stars, open star clusters, and the vast molecular clouds where new stars are born. This thin disk is only about 700 light-years thick, a remarkably slim structure considering the galaxy's 100,000 light-year diameter. Above and below this thin disk lies the thick disk, older, puffier, and more diffuse. Stars in the thick disk tend to be several billion years old, formed during an earlier era of the galaxy's history. They contain fewer heavy elements than stars in the thin disk, and they move in orbits that are more tilted and elliptical. This suggests the thick disk formed under different conditions, possibly stirred and heated by ancient galactic collisions or migrations of massive clumps of dark matter through the disk. The galaxy's structure is not uniform. It is textured, layered, and shaped by time, like sediment that has settled on the floor of a cosmic ocean. Understanding the thick and thin disks helps astronomers piece together the Milky Way's history, revealing how it assembled over billions of years from smaller building blocks. The galaxy's magnetic field threads through the disk. Though invisible to the eye, the Milky Way is laced with a vast magnetic field that stretches across the disk, rises into the halo, and weaves through the interstellar medium like an intricate web. This field is weak by earthly standards, thousands of times fainter than the magnetic field at Earth's surface. But over galactic distances, it becomes significant. The magnetic field shapes how cosmic rays travel, bending the paths of charged particles as they stream through space. It influences how gas clouds collapse and how material flows through the galaxy. The field aligns with the spiral arms, forming arcs above the plane and twisting into loops that defy simple explanation. Studying the galactic magnetic field requires radio telescopes and careful analysis of polarized light from distant stars. But its presence is unmistakable. The Milky Way does not just glow with light, it breathes with magnetism, a subtle pulse running through its structure. The origin of this magnetic field is still debated. It may be generated by the motion of ionized gas in the disk, similar to how Earth's magnetic field is created by currents in its molten core. Or it may be amplified by dynamo processes involving turbulence and differential rotation. Whatever the cause, the magnetic field plays a crucial role in the galaxy's dynamics and evolution. The interstellar medium is full of invisible structures. Between the stars lies more than emptiness. The interstellar medium, a thin mixture of gas, dust, and plasma, weaves its way through the Milky Way like a cosmic fog. To the naked eye, most of it is invisible. But when viewed with radio telescopes, infrared cameras, and X-ray detectors, it reveals stunning complexity. The interstellar medium forms filaments, bubbles carved by supernova explosions, shock waves rippling through space, and cold, dense clouds where stars are born. Supernovae carve vast cavities in the medium, creating hot, low-density regions surrounded by shells of compressed gas. Stellar winds from massive stars sculpt the medium into shapes that ripple across light years. The space between stars is not a void, but a shifting web of matter and magnetism, the quiet fabric from which galaxies evolve and life eventually begins. The interstellar medium is not static. It is constantly stirred by stellar winds, heated by radiation, compressed by shock waves, and cooled by radiative processes. Different regions have vastly different properties. Some areas are cold and dense, perfect for star formation. Others are hot and tenuous, blown clear by supernovae or stellar winds. This complex, dynamic medium is essential to understanding how galaxies function and evolve. Cosmic rays constantly pass through us from the galaxy. Every second, without your awareness, high-energy particles stream through your body. These are cosmic rays, mostly protons and atomic nuclei, accelerated to nearly the speed of light by shock waves from supernova explosions or other energetic events in the galaxy. They travel through space, bending around magnetic fields, bouncing off gas clouds, and occasionally colliding with atoms in Earth's atmosphere. When they do, they create cascading showers of secondary particles that rain down on the surface. Most of the time, we do not notice them. But they carry stories from across the galaxy, evidence of ancient supernovae, traces of distant acceleration mechanisms, messages from the violent deaths of stars. Even as you rest, the galaxy is whispering in particles, in silence, in rays of light we cannot see. Cosmic rays are one of the ways we know about the high-energy processes occurring throughout the Milky Way. By detecting and analyzing them, scientists learn about supernova remnants, pulsar wind nebulae, and even the distribution of dark matter. Cosmic rays also play a role in the chemistry of the interstellar medium, ionizing molecules and triggering chemical reactions that would not occur otherwise. The galaxy is not symmetrical. Though many diagrams show the Milky Way as a neat, even spiral with perfectly balanced arms, the reality is more complex. One side of the disk appears thicker than the other. Some spiral arms are brighter, longer, or more curved than their counterparts. The warp in the outer disk is lopsided, with one side bending upward more than the other side bends downward. Even the count of stars between hemispheres is slightly off, revealing subtle asymmetries. These irregularities may be caused by past gravitational encounters with smaller galaxies, by the influence of dark matter clumps moving through the galaxy, or by the ongoing interaction with satellite galaxies, like the large and small Magellanic Clouds. They remind us that galaxies, like living things, carry traces of their histories in their shapes. Scars of collisions, wrinkles of time, and quirks of uneven growth give them character and depth. The Milky Way is not a perfect textbook spiral. It is a real complex structure, shaped by billions of years of dynamic evolution. The oldest known stars in the galaxy may live in the halo. High above the galactic plane, drifting through the vast spherical halo, astronomers have discovered stars that may be nearly as old as the universe itself. These ancient suns contain almost no heavy elements, a signature of stars born soon after the Big Bang, before multiple generations of supernovae had enriched the cosmos with carbon, oxygen, and iron. Some of these stars formed over 13 billion years ago, when the Milky Way was just beginning to assemble from primordial gas clouds. They burn quietly now, with a soft red glow, low in mass, but rich in history. They are not just stars, they are time capsules, living relics from the universe's earliest dawn, witnesses to epochs we can study in no other way. By analyzing their chemical compositions and measuring their ages, astronomers peer back to a time when galaxies were just forming, when the first heavy elements were just beginning to appear, and when the universe was a very different place. These stars have survived for eons, outliving countless generations of more massive stars, and they will continue to shine for trillions of years more, long after our sun has faded into a cold white dwarf. The center of the galaxy spins faster than the outskirts. In the inner regions of the Milky Way, closer to the supermassive black hole and the dense stellar bulge. Stars orbit the galactic center much more rapidly than those farther out. Near the core, the gravitational pull is immense, packed with mass from billions of stars, clouds of gas, and the 4 million solar mass black hole itself. This causes stars in the inner regions to sweep through tighter, faster orbits, completing revolutions in just a few million years. Out in the quieter suburbs of the galaxy, where our Sun resides, stars orbit more slowly, taking 225 million years or more to complete a single circuit. This uneven rotation creates twisting patterns, stretches the spiral arms, and keeps the disk from behaving like a solid, rigid structure. The galaxy moves like a great wheel, but one whose rim lags behind its hub. This differential rotation is a fundamental characteristic of spiral galaxies and plays a key role in shaping their structure and evolution. It also contributes to the winding and amplification of the galactic magnetic field through a process known as the galactic dynamo. Spiral arms are shaped by density waves. The spiral arms of the Milky Way are not permanent trails of stars frozen in place. They are density waves, regions where matter temporarily becomes more concentrated as it moves through the disk. Picture a traffic jam on a highway. Individual cars enter the jam, slow down, and then exit. But the jam itself moves at a different speed and can persist even as different cars pass through it. Spiral arms work similarly. As gas and dust pass through these density waves, they are compressed by the increased gravitational pull. This compression triggers the collapse of molecular clouds and the formation of new stars. The newly born stars, especially the massive, hot blue ones, light up the arms with brilliant light. These massive stars have short lifetimes, only a few million years, so they do not drift far before exploding as supernovae. This keeps the spiral arms well-defined and luminous. Lower mass stars like our Sun live much longer and have time to drift out of the arms, blending into the general stellar population. The arms themselves move through the disk like waves on the ocean, persistent patterns that shape the distribution of matter and star formation across the galaxy. The origin of these density waves is still debated, but they may be driven by gravitational interactions with satellite galaxies, by instabilities in the disk itself, or by the influence of the central bar. Stars are born from cold, collapsing gas. In the darkest corners of the Milky Way, star formation begins in silence. Massive clouds of molecular hydrogen, chilled to just a few degrees above absolute zero, drift through space, sometimes spanning hundreds of light years. These clouds are among the coldest places in the universe, far colder than the void of intergalactic space. Within these frigid clouds, gravity slowly takes hold. Tiny perturbations, perhaps triggered by a passing shockwave from a supernova or the compression of a spiral arm density wave, cause certain regions to grow denser. As the gas falls inward, the density and temperature begin to rise. The collapsing material forms a spinning disk around a growing protostar at the center. Over time, perhaps a few 100,000 years for a star like our Sun, the core temperature and pressure climb until nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing enormous amounts of energy, and a new star is born. From the coldest shadows come the brightest lights, spun gently into being by the quiet, patient force of gravity. Each star that forms may be accompanied by a disk of leftover material that can coalesce into planets, moons, asteroids, and comets, creating entire solar systems from the remnants of the star-forming process. Star clusters can dissolve into the galactic field. Many stars are born not in isolation, but in groups, tight clusters formed from the same collapsing gas cloud. These clusters, bound together by mutual gravity, drift through the galaxy as cohesive units for millions or even billions of years. But over time, they begin to scatter. Tidal forces from the Milky Way's immense mass, close encounters with other stars or molecular clouds, and internal gravitational interactions all work to pull clusters apart. Stars peel away one by one, like leaves falling from a tree, until the cluster fades into the general star field of the galaxy. Even our Sun was likely born in a stellar cluster long ago. Its siblings, once numbering in the hundreds or thousands, have now scattered across the galaxy, dimmed by distance, lost in the haze of billions of other stars. The galaxy is filled with the remnants of dissolved clusters, stars that once shared a common origin, but now drift independently through space. By studying the motions and chemical compositions of nearby stars, astronomers can sometimes identify groups that were once part of the same cluster, tracing their shared heritage even after they have dispersed. These stellar families tell us about the conditions in which the Sun and Solar System formed, and about the dynamic processes that shape the galactic disk over time. The galaxy contains ancient hypermetal-poor stars. Among the rarest and most precious objects in the Milky Way are hypermetal-poor stars. These ancient suns contain almost no elements heavier than helium, with iron abundances less than 1/10,000th that of the Sun. They are believed to be among the first stars born after the very first generation of massive stars, which astronomers call Population 3 stars, lived and died. Population 3 stars, if they existed, were composed entirely of hydrogen and helium from the Big Bang. When they exploded as supernovae, they scattered the first heavy elements into space, enriching the gas from which the next generation would form. Hypermetal-poor stars carry only faint traces of this early enrichment, preserving a chemical signature from the universe's infancy. They are incredibly old, more than 13 billion years in some cases, and scattered in the halo like distant lanterns from the dawn of time. Each one is a kind of relic, a glowing, gravitationally bound signature from a near-forgotten epoch when galaxies were just beginning to coalesce, and the universe looked very different than it does today. Studying these stars helps astronomers understand the conditions in the early universe, the nature of the first stars, and the processes that led to the chemical enrichment of galaxies. Planetary systems form throughout the Milky Way. Planets are not a rare or unusual feature of the cosmos. They are a natural consequence of star formation, arising from the same disks of gas and dust that surround newborn stars. As a young star ignites at the center of a rotating disk, particles in the disk begin to stick together. Dust grains collide and merge into pebbles. Pebbles accumulate into boulders. Boulders grow into planetary embryos. Over millions of years, these embryos sweep up material from their surroundings, becoming planets. Across the Milky Way, this process has repeated countless times. Planetary systems are common, perhaps the rule rather than the exception. Some systems contain gas giants like Jupiter, massive worlds wrapped in thick atmospheres of hydrogen and helium. Others harbor rocky terrestrial planets, some perhaps resembling Earth. Still others may have exotic configurations we have yet to imagine. Ice giants, lava worlds, planets orbiting binary stars, rogue planets drifting alone through interstellar space. The diversity is staggering. The galaxy is not just full of stars, it is full of worlds, entire solar families, each one with its own unique balance, architecture, and potential. Recent surveys suggest that nearly every star in the galaxy hosts at least one planet on average. meaning there may be hundreds of billions of planets in the Milky Way alone. Earth orbits near the corotation radius. In the Milky Way, the spiral arms rotate at a different speed than individual stars, creating a pattern that moves through the disk like a wave. But there is a special distance from the galactic center called the corotation radius, where the speed of stars in their orbits matches the rotation speed of the spiral arms themselves. Our Sun orbits close to this boundary, drifting in a region where we avoid frequent crossings of the spiral arms. This gentle synchronization may be significant. Spiral arms are places of higher star density, more frequent supernovae, and greater gravitational disturbances. By orbiting near the corotation radius, the solar system may have enjoyed a more stable environment over billions of years, shielded not by walls, but by a fortunate resonance in motion. This stability could have been important for the development of life on Earth, providing long periods of relative calm without catastrophic nearby supernovae or intense radiation bursts. It is one of many factors that may have made Earth a suitable home for life, a cosmic coincidence that placed us in a safer neighborhood of the galaxy. The Sun bobs up and down through the galactic plane. As it orbits the Milky Way, the Sun does not follow a perfectly flat path confined to the disk. Instead, it moves in a gentle wave, drifting above and below the galactic plane, like a cork bobbing in slow motion on an ocean. This vertical oscillation takes tens of millions of years to complete one full cycle. The motion is caused by the gravitational tug of the galaxy's mass, pulling the solar system back toward the midplane whenever it strays too far above or below. Currently, the Sun is slightly above the galactic plane and moving upward, but it will eventually reach a peak and begin descending back toward the midplane. Some researchers have speculated that this oscillation might influence long-term climate patterns or extinction events on Earth, though the evidence remains inconclusive. The idea is that, when the solar system passes through the denser regions of the galactic plane, it might encounter more interstellar dust or be more vulnerable to gravitational perturbations that could disturb the Oort cloud, a distant shell of comets surrounding the Sun. These disturbances could potentially send comets plunging into the inner solar system, increasing the risk of impacts. However, the effect, if any, is subtle and difficult to detect in the geological and fossil records. We do not know exactly what dark matter is, but we know it is there. Dark matter makes up most of the Milky Way's mass, yet it has never been seen directly. It does not emit light, absorb light, or reflect light in any way we can measure. It passes through ordinary matter as if it were not there, interacting only through gravity. But its gravitational effects are unmistakable, written in the motions of stars and gas throughout the galaxy. Without dark matter, the Milky Way's rotation curve, the way orbital speeds change with distance from the center, makes no sense. The visible matter alone cannot account for the observed velocities. Stars in the outer regions should be moving much more slowly if only the mass we can see were present. Yet they orbit quickly, held in place by the gravitational pull of something unseen. This invisible substance surrounds the galaxy in an enormous halo, extending far beyond the visible disk and containing perhaps 10 times as much mass as all the stars, gas, and dust combined. Astronomers detect dark matter not by seeing it, but by watching how it moves other things. By measuring the bending of light around massive clusters of galaxies, by analyzing the cosmic microwave background, and by studying the large-scale structure of the universe. Despite decades of searching, the true nature of dark matter remains one of the greatest mysteries in science. Is it composed of exotic particles that barely interact with ordinary matter? Is it primordial black holes formed shortly after the Big Bang, Or is it something else entirely? Perhaps a sign that our understanding of gravity itself is incomplete. The answer remains elusive, but the search continues. There is more mass outside the disk than inside. Most of the Milky Way's visible stars lie within the flat, luminous disk, the spiral structure we can see arcing across the night sky. But the majority of the galaxy's mass resides elsewhere, hidden from view. The dark matter halo that surrounds the Milky Way is enormous, stretching far beyond the furthest stars and globular clusters, extending for hundreds of thousands of light years. This halo holds most of the galaxy's mass, outweighing the disk and bulge by a large margin, perhaps by a factor of 10 or more. It is populated sparsely with ancient stars and globular clusters, but its true bulk is invisible, composed of dark matter. When we think of the Milky Way, we picture its spiral arms and glowing center. But that is only the luminous surface, the visible tip of a much larger structure. The mass that defines the galaxy, its gravity, its motion, its reach, is mostly hidden, enveloping everything like a quiet shroud. This realization has profound implications for our understanding of galaxy formation and evolution. It suggests that galaxies are fundamentally dark matter structures, with visible matter merely settling into the gravitational wells created by dark matter halos. The Milky Way's core may have flared as a quasar in the past. Today, the supermassive black hole at the heart of our galaxy appears quiet, accreting material slowly and emitting relatively little light. But there is evidence that it was once far more active. The presence of enormous gamma-ray structures, like the Fermi bubbles, along with traces of high-energy light reflected in surrounding gas clouds, suggests that Sagittarius A** may have flared dramatically in the past. If the black hole received a sudden influx of gas, perhaps from a molecular cloud falling inward, or from a star wandering too close and being torn apart, it could have lit up as a quasar. Quasars are among the brightest objects in the universe, powered by supermassive black holes actively feeding on vast amounts of material. The intense radiation from an accretion disk around the black hole can outshine all the stars in the galaxy combined. If the Milky Way once burned like this, it would have looked dramatically different, a spiral wrapped around a blinding heart of light. That era has passed, but the echoes remain, frozen in the structure of the Fermi bubbles and the chemistry of gas clouds surrounding the core. Understanding this past activity helps astronomers reconstruct the history of our galaxy and the evolution of its central black hole. The galaxy's structure changes over billions of years. Galaxies may look timeless in photographs, frozen in elegant spirals or smooth ellipses, but they are constantly evolving. Spiral arms shift their positions. Bars form, dissolve, or rotate. Gas flows inward and outward, driven by stellar winds, supernova explosions, and gravitational interactions. Stars are born and die, altering the chemical composition and appearance of the galaxy. Even the shape of the Milky Way's disk, with its warp, ripples, and asymmetries, is slowly changing. Encounters with dwarf galaxies and the pull of dark matter clumps can bend or twist the structure. Over billions of years, the galaxy's silhouette shifts like a drifting cloud. The Milky Way of today is not the same galaxy that existed 10 billion years ago, and it is not the galaxy that will exist 10 billion years in the future. Its beauty lies not in permanence, but in quiet transformation, an ongoing process of assembly, destruction, and renewal played out over cosmic timescales. The merger with Andromeda will be the most dramatic change, fundamentally altering the structure and appearance of our galactic home. But even before that, smaller changes accumulate, reshaping the Milky Way slowly and inexorably. Gravitational waves ripple through the galaxy from distant mergers. All across the universe, massive objects collide. Black holes spiral together and merge. Neutron stars crash in spectacular kilonova explosions. Entire galaxies slam into one another across billions of light years. These violent events send out gravitational waves, ripples in the very fabric of space-time itself. Though incredibly faint by the time they reach us, some of these waves pass through the Milky Way, distorting space by tiny amounts as they travel at the speed of light. They are so subtle that it took scientists decades to develop instruments sensitive enough to detect them. The first gravitational wave was observed in 2015, opening an entirely new window on the universe. Now, observatories like LIGO and Virgo regularly capture these cosmic tremors, listening to the universe in a way that was impossible before. Even now, as you rest, space itself is shifting ever so slightly. Not enough to feel, but enough to tell us that somewhere far away, the universe is changing. Gravitational wave astronomy is still in its infancy, but it has already revealed phenomena that were previously invisible, including the merger rates of black holes and neutron stars, the properties of ultra-dense matter, and tests of general relativity under extreme conditions. Some stars orbit in elongated, tilted paths. Not all stars move in neat, circular orbits around the galactic center. Some follow long, stretched ellipses, their paths looping high above and far below the disk, tilted at odd angles from the main plane. These eccentric orbits likely come from different origins. Some stars may be relics of dwarf galaxies swallowed by the Milky Way billions of years ago, retaining the unusual orbital characteristics of their former homes. Others may have been scattered into tilted paths by gravitational encounters with massive objects, or by the disruption of their birth clusters. These misaligned stars are clues, three-dimensional maps of the galaxy's chaotic past. By tracing their motion through space, astronomers reconstruct the invisible architecture of the Milky Way's mass distribution and its long history of mergers. These stars drift like messengers from disrupted systems, tilted and stretched, but still bound to the whole. Their orbits encode information about ancient collisions and the distribution of dark matter in ways that stars with more ordinary paths do not. Each unusual orbit is a piece of the puzzle, helping scientists understand how the galaxy assembled itself from smaller pieces over cosmic time. The Milky Way emits neutrinos we can barely detect. Every second, trillions of neutrinos pass through your body, straight through the Earth and out the other side without even slowing down. These ghostly particles are produced in nuclear reactions deep within stars, in supernova explosions, and when cosmic rays strike atoms in the interstellar medium. The Milky Way is bathed in them, a constant stream of nearly massless particles that interact so weakly with ordinary matter that they slip through almost everything unimpeded. They are so elusive that it takes enormous detectors buried deep underground or under ice to catch just a few. When a neutrino does interact with an atom, it produces a flash of light that sensitive instruments can detect. These rare events allow scientists to study processes happening deep inside stars or in the cores of supernova explosions, places no telescope can see because light cannot escape. Neutrinos carry information from the hidden interiors of cosmic furnaces, from stellar cores where fusion occurs, from collapsing stars moments before they explode, and from the galaxy's unseen energy reservoirs. They are the whispers of cosmic fire, messengers from realms we cannot observe any other way. In 2023, astronomers announced the first detection of neutrinos originating from the galactic plane itself, creating the first neutrino map of the Milky Way and revealing the galaxy in an entirely new form of light. Interstellar space is not empty but turbulent. Between the stars, space is not smooth or still. The interstellar medium, that thin mixture of gas and dust filling the voids, is stirred by shock waves from supernovae, heated by stellar radiation, compressed by spiral arms, and twisted by magnetic fields. Temperature can vary wildly from region to region. In some areas, the gas is so cold it hovers just a few degrees above absolute zero. In others, it is heated to millions of degrees by supernova shocks or stellar winds. Flows of material collide and mix. Clouds stretch, fold, and tumble. On large scales, this creates a kind of turbulence, like a slow-motion ocean swirling through the disk. Star formation, the propagation of cosmic rays, and even galactic evolution itself are all affected by this restless sea. What looks from afar like calm starlight is, up close, a dynamic, rippling fabric shaped by invisible winds and ancient energy. The interstellar medium is not passive. It responds to the galaxy's rhythms, absorbing energy from dying stars, redistributing matter across vast distances, and providing the raw material for future generations. It is the circulatory system of the galaxy, constantly in motion, constantly recycling. The galactic halo may contain rogue planets. Planets are not always tethered to stars. Some form normally within protoplanetary disks, but are later ejected from their systems during gravitational interactions. Others may never have had a star at all, forming in isolation from collapsing clouds of gas or being torn away from their parent stars so early in their development that they never truly belonged to a solar system. These are rogue planets, worlds adrift in the galaxy, cold, dark, and alone. Though incredibly difficult to detect because they emit no light of their own and reflect no starlight, studies suggest there may be billions of them wandering through the Milky Way. Some may even lurk in the outer halo, far from the galactic plane, where stars are few and far between. Without light or warmth from a sun, they float unseen, heated only by internal radioactive decay or leftover heat from their formation. They are orphans of the galaxy, planetary drifters following long, lonely paths through the darkness between stars. Some may retain thick atmospheres that insulate them, trapping enough heat to maintain subsurface oceans beneath frozen crusts. Others might be barren ice balls or rocky cores, relics of disrupted planetary systems. Magnetic fields shape the flow of cosmic dust. Interstellar dust, those tiny grains of carbon, silicon, and ice, does not drift randomly through space. It moves under the influence of the galaxy's magnetic field, which threads through the disk and halo like invisible currents. These fields guide the motion of charged particles and influence how gas and dust align and accumulate. In some regions, dust grains spin rapidly, emitting faint microwave radiation that astronomers can detect. In others, the grains align themselves with magnetic field lines, polarizing the starlight that passes through them. By studying this polarization, scientists can trace the structure and strength of the galactic magnetic field across vast distances. Understanding these effects helps astronomers map the three-dimensional architecture of magnetism in the Milky Way, and even remove its influence from studies of the cosmic microwave background, the faint afterglow of the Big Bang. Dust is not passive. It dances to a magnetic rhythm, falling into hidden patterns shaped by forces we cannot see. This magnetic influence extends to star formation as well. Magnetic fields can support clouds against gravitational collapse, or channel material into dense filaments where stars more easily form. Some stars are enriched by neutron-star collisions. When two neutron stars spiral together and collide, they create one of the most violent events in the universe, a kilonova. In this brief, blinding explosion, lasting only days, enormous quantities of heavy elements are forged in conditions of unimaginable density and temperature. Gold, platinum, uranium, and other elements beyond iron are created in the intense, neutron-rich environment of the merger and scattered into space. These materials mix with the interstellar gas and eventually become incorporated into new generations of stars and planets. Some stars in the Milky Way carry the chemical fingerprints of these rare events, enriched in elements that could only have been created in neutron-star collisions. They are not just luminous bodies, but record-keepers of ancient cataclysms, burning with the residue of stellar wreckage and cosmic alchemy. The gold in your jewelry, the platinum in catalytic converters, the uranium used for nuclear power, all of it was likely created in neutron-star mergers billions of years ago, and eventually found its way into the cloud of gas that formed our solar system. Every heavy element in your body tells a story of cosmic violence and creation. The Milky Way may have a hidden bar within a bar. At the heart of the galaxy lies a prominent bar of stars crossing the central bulge, rotating slowly and funneling gas toward the supermassive black hole. But deep within that bar, astronomers have found hints of another, smaller bar, tilted at a different angle and rotating independently. This inner structure, sometimes called a nuclear bar, is difficult to see directly because it is obscured by dust and distance. But its gravitational influence appears in the motion of nearby stars and gas. Such nested bars are not unique to the Milky Way. They have been observed in other galaxies and are thought to play an important role in channeling material inward, feeding central black holes, and triggering bursts of star formation in galactic cores. The Milky Way's center is not one simple shape. It is a layered, shifting labyrinth of gravitational structures, each influencing the flow of matter and the evolution of the inner galaxy. These nested bars can create complex resonances, regions where the gravitational pulls of the two bars combine in ways that either enhance or suppress star formation. Understanding this intricate architecture helps explain the distribution of stars and gas in the central kiloparsec of the galaxy. Gas inflows feed the galaxy from the cosmic web. The Milky Way is not a closed system, sealed off from the rest of the universe. It draws in fresh gas from the intergalactic medium, those long, tenuous streams flowing through the vast cosmic web that connects galaxies across the universe. These inflows provide the raw material for new stars, replenishing what the galaxy loses over time through stellar winds, supernova explosions, and other processes that eject gas into the halo or beyond. Some gas arrives as cold filaments, slipping quietly into the disk along paths of least resistance. Other streams fall in as hot, shock-heated material, lighting up in ultraviolet or X-ray wavelengths as they collide with gas already present in the halo. These invisible rivers sustain the galaxy's growth and evolution, linking it to the larger cosmic structure beyond. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter spun from the early universe. This accretion is not constant. It varies with time and depends on the large-scale environment. Galaxies in dense clusters, for example, may have their gas supplies cut off by interactions with hot intra-cluster gas, quenching star formation. Isolated galaxies like the Milky Way can continue to accrete material for billions of years. Hot gas bubbles form chimneys out of the disk. When clusters of massive stars go supernova, they create enormous cavities in the interstellar medium, carving out regions of hot, low-density gas. These bubbles can join together, forming what astronomers call superbubbles, vast pockets of gas heated to millions of degrees. In some cases, these structures punch upward through the galactic disk, creating chimneys or channels where energy, gas, and magnetic fields vent into the halo. The result is a kind of galactic fountain, with hot gas rising from the disk, cooling as it ascends, and eventually raining back down over millions of years. These chimneys regulate the pressure of the interstellar medium, redistribute metals created in stars, and help shape the structure of the halo. The galaxy, in this way, breathes not just within the disk, but through towering columns that carry its energy up and out into the dark. This circulation is essential for understanding the galaxy's ecology. Without these venting mechanisms, the disk would become overpressured and unstable. The chimneys allow energy to escape, maintaining a balance between heating from supernovae and cooling from radiation. The galaxy shines in X-rays from old stars and black holes. Though the Milky Way appears calm in visible light, a serene spiral of stars and gas, it glows fiercely in other wavelengths. X-rays pour from its core, from the region around Sagittarius A*, from collapsed stellar remnants like neutron stars and white dwarfs, and from the edges of black holes where matter spirals inward at tremendous speeds. White dwarfs in binary systems can siphon matter from companion stars, heating it to millions of degrees before it crashes onto their surfaces. Neutron stars in similar configurations create intense X-ray emissions as accreted material releases gravitational energy. Hot gas in the halo, heated by supernova shocks and stellar winds, also emits faint X-rays that reveal the galaxy's larger skeleton. We cannot see this high-energy light with our eyes, but telescopes like Chandra and XMM Newton paint a very different portrait of the Milky Way. Not a tranquil spiral, but a realm of extreme temperatures, compact remnants, and hidden radiation. The X-ray sky shows us the violent, energetic processes that complement the calmer view we see in optical light. It reveals the endpoints of stellar evolution and the regions where gravity and energy reach their most extreme expressions. Pulsars act as cosmic clocks throughout the Milky Way. When a massive star dies and collapses into a neutron star, it may be left spinning incredibly fast, with beams of radiation sweeping across space like a lighthouse. These are pulsars, and some rotate hundreds of times per second, pulsing with such regularity that they rival atomic clocks in precision. They are so consistent that astronomers use them as cosmic timekeepers, tracking their signals to measure distances, test theories of gravity, and even search for gravitational waves. Across the Milky Way, pulsars blink quietly, remnants of stellar death, but also beacons of astonishing order. They keep time, not for minutes or days, but for entire epochs, ticking steadily in the silence between stars. The fastest pulsars, called millisecond pulsars, were spun up by accreting matter from companion stars, like cosmic tops given a fresh twist. Their rotation rates are so stable that astronomers have created pulsar timing arrays, networks of pulsars monitored over years, to detect the subtle perturbations caused by passing gravitational waves. These arrays have recently begun detecting the background hum of gravitational waves permeating the galaxy, a discovery that opens yet another window on cosmic phenomena. Radio waves map the hidden structure of the galaxy. Much of the Milky Way is invisible in optical light, hidden by thick clouds of dust, obscured by distance, or simply too faint to see. But radio waves can slip through these barriers, revealing structures otherwise unseen. They trace cold hydrogen gas, the most abundant element in the universe, outlining the distribution of material across the entire galactic disk. Radio emissions also highlight regions of active star formation, supernova remnants still glowing with residual energy, and pulsar signals ticking away in the darkness. Using arrays of radio telescopes working together, astronomers have mapped the spiral arms, measured the warp of the disk, and discovered star-forming regions cloaked in dust. Where optical light is blocked, radio waves let us see. The galaxy speaks in frequencies we cannot hear, but one that science has learned to translate into maps of shape, motion, and shadow. Radio astronomy has revealed the Milky Way's large-scale structure in ways that optical observations never could, showing us the true extent and complexity of our galactic home. The Sun was likely born in a stellar cluster. Stars rarely form in solitude. They are usually born in groups, stellar clusters, shaped from the same collapsing molecular cloud. Our Sun was almost certainly one of these, formed about 4.6 billion years ago, in a nursery containing hundreds, perhaps thousands, of sibling stars. These stars would have been bound together by mutual gravity for a few million years, drifting through space as a loose association. But over time, gravitational interactions with other objects, tidal forces from the galaxy, and the random motions of individual stars gradually dispersed the cluster. The Sun's siblings scattered across the Milky Way, each following its own path. Today, they are lost among billions of other stars, indistinguishable except through careful analysis of their ages, chemical compositions, and motions through space. Some may still shine nearby, invisible among the crowd. Others have drifted far, flung into different spiral arms, or even into the halo. The Sun's birth cluster is gone, dissolved into the galactic field. But the memory of that shared origin remains encoded in the chemistry of the solar system, and perhaps in the properties of other stars born from the same cloud. The Sun's siblings are scattered across the galaxy. Though the Sun's birth cluster dissolved long ago, astronomers are actively searching for its lost siblings, stars that share its age, chemical fingerprint, and perhaps its motion through the galaxy. Using vast surveys like Gaia, which has measured the positions and velocities of nearly 2 billion stars, and spectroscopic databases that analyze stellar compositions, researchers hope to identify these long-lost relatives. A few candidates have emerged over the years, stars that may have been born from the same molecular cloud as the Sun. If confirmed, they could reveal important details about the conditions in which the Sun and the early solar system formed, including the density of the birth cluster, the presence of nearby massive stars, and the chemical composition of the original gas cloud. Our place in the galaxy is not entirely solitary. Somewhere out there, scattered across thousands of light years, the Sun's ancient kin may still shine, carrying within them the same elemental signature that marks them as family. Finding them would be like discovering distant cousins we never knew existed, separated by time and space, but linked by a common origin. The galactic disk wobbles as it spins. The Milky Way's disk is not a perfectly flat, rigid structure. It wobbles gently, rippling like a spinning plate nudged off balance. This wobble is most visible in the outer regions, where the disk bends upward on one side and downward on the other, creating a wave that propagates through the stars and gas. The warp may be caused by the gravitational influence of nearby dwarf galaxies, particularly the large and small Magellanic Clouds, which tug on the Milky Way's edges as they orbit. Alternatively, clumps of dark matter passing through or beneath the disk could create similar distortions. The wobble rotates slowly over hundreds of millions of years, like a vast wave moving through the stars, From Earth, we do not feel it, but from a distance, the Milky Way would appear as a dynamic, undulating sheet of stars, curving gently as it turns. This discovery reminds us that galaxies are not static sculptures. They are living, breathing structures that respond to internal and external forces, bending and flexing over cosmic timescales. Galactic tides can distort star clusters and streams. Just as the Moon's gravity pulls tides on Earth's oceans, the immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters, satellite galaxies, and even globular groups feel the galaxy's uneven gravitational pull, which is stronger on the side closer to the galactic center than on the far side. Over time, these tidal forces can stretch and distort structures, drawing out long stellar streams or peeling stars away from their orbits. Many of the faint arcs of stars mapped across the sky are remnants of such encounters, clusters in the process of being unraveled, or galaxies slowly torn apart. The galaxy does not break these structures suddenly. It unravels them patiently, strand by strand, over millions of years. The streams left behind trace the orbits of the disrupted objects, providing clues to the distribution of mass in the Milky Way, including the dark matter halo. By studying these streams, astronomers can map the gravitational landscape of the galaxy and test models of how dark matter is distributed. The Milky Way's mass is still uncertain. You might think we would know the mass of our own galaxy with great precision, but measuring it is remarkably difficult. Stars and gas make up only a small portion of the total. The rest lies in the vast, dark matter halo, which we cannot see directly. Estimates of the Milky Way's total mass vary considerably, depending on the methods used and the assumptions made. Some studies suggest a mass close to 1 trillion times that of the Sun. Others place it much higher, possibly exceeding 1.5 trillion solar masses. The uncertainty comes from trying to measure how fast objects orbit at great distances, a task clouded by limited data and the pervasive influence of invisible matter. Globular clusters, satellite galaxies, and stellar streams all provide clues, but piecing together the full picture remains challenging. The Milky Way is our home, yet its weight remains a quiet mystery, a fundamental property we are still working to pin down. Future surveys with improved measurements of distant objects will gradually reduce these uncertainties, but for now, the galaxy's mass remains one of the key unknowns in our understanding of the Milky Way's structure and evolution. The Milky Way may be heavier than Andromeda. For many years, astronomers assumed that the Andromeda galaxy, slightly larger and brighter than the Milky Way, was also more massive. But recent measurements suggest that the Milky Way's dark matter halo may be broader and denser than previously believed, potentially giving our galaxy more total mass despite its more modest visible appearance. If true, this would mean the Milky Way outweighs Andromeda, a surprising reversal of expectations. This matters not only for comparisons, but also for predictions about the eventual merger. When the two galaxies collide in about 4.5 billion years, their relative masses will shape the dynamics of the encounter, determining which galaxy dominates and what the final structure will look like. The Milky Way may look gentle, a serene spiral in the night sky, but beneath its quiet arms, it carries more weight than we once imagined. This revelation came from studies of the velocities of satellite galaxies and stellar streams, which revealed stronger gravitational pulls than expected, implying more mass in the Milky Way's halo. The Magellanic Clouds may be on their first orbit. The Large and Small Magellanic Clouds, two bright satellite galaxies visible from the southern hemisphere, have long been thought to orbit the Milky Way in stable, repeating paths. But new evidence suggests they may be newcomers, captured only recently in cosmic terms, and possibly on their first close pass around our galaxy. Their velocities and motions through space hint that this could be their first orbit, not a long-standing companionship. If true, they are not ancient satellites, but distant wanderers just now falling under the Milky Way's pull. Their arrival has stirred the outer disk, contributing to the warp, and possibly triggering bursts of star formation through gravitational interactions. The sky, it turns out, is full of first encounters, galaxies meeting for the first time in the long expanse of cosmic history. The Magellanic Clouds are connected by a bridge of gas and stars, evidence of their mutual interaction, and they trail a long stream of hydrogen gas called the Magellanic Stream, which stretches across a significant portion of the sky. This stream may eventually fall into the Milky Way, providing fresh fuel for star formation. The Magellanic Stream is a ribbon of stripped gas. Trailing behind the Magellanic Clouds is a vast ribbon of hydrogen gas known as the Magellanic Stream. This structure stretches over hundreds of thousands of light years, wrapped in curves and arcs across the southern sky. It was pulled away by tidal forces as the dwarf galaxies passed close to one another and to the Milky Way, a slow gravitational stripping that continues today. Invisible in optical light, the stream reveals itself in radio wavelengths, a long, trailing whisper of motion and loss. This gas may one day feed new star formation in the Milky Way, settling into the disk and joining the cycle of stellar birth and death. Or it may continue to stretch and disperse, becoming part of the diffuse gas that fills the space between galaxies. The stream is a record of interaction, a visible reminder that even on cosmic scales, proximity leads to influence, and nothing remains entirely untouched. Studying the Magellanic Stream helps astronomers understand the dynamics of the Milky Way and its satellites, as well as the processes that strip gas from smaller galaxies. Some gas clouds orbit in polar directions. Not everything in the Milky Way follows the neat plane of the disk. Some clouds of gas, and even some stars, move in highly inclined orbits, passing above and below the galaxy's main structure at steep angles. These polar orbits likely come from past mergers, when dwarf galaxies or stray clouds were captured at odd angles and retained their unusual trajectories. Over time, they continue to orbit on tilted paths, looping through the halo like comets circling a planet. These misaligned objects are records of disruption, visible reminders that the galaxy is not a closed, orderly system, but an evolving structure shaped by the unpredictable flow of cosmic history. Each unusual orbit tells a story, encoding information about ancient collisions and the chaotic processes that built the Milky Way from smaller pieces. By mapping these polar orbits, astronomers reconstruct the merger history of our galaxy and learn about the three-dimensional distribution of mass. Giant shells of gas surround past starbursts. In several regions of the Milky Way, astronomers have found enormous spherical shells of gas, some spanning hundreds of light years. These shells are the remnants of powerful starbursts, episodes when clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined winds and supernova carved out huge cavities in the interstellar medium, blowing gas outward in all directions. Over time, the expansion slows as the shells encounter more material, but they remain as ghostly bubbles marking where the galaxy once burned bright with stellar birth and death. These are the fossils of cosmic fireworks, still echoing in the cold. The shells compress the gas they sweep up, and in some cases, this compression can trigger new waves of star formation at their edges. This creates a cycle of sequential star formation, where one generation of stars triggers the birth of the next. Stars occasionally collide in dense regions. Space is vast and stars are small, making collisions extremely rare. But in the densest regions of the Milky Way, such as the cores of globular clusters or the crowded central bulge, stars can pass close enough to interact and even merge. When two stars collide, the result can be dramatic. A burst of energy, the merging of two suns, or the formation of a rare stellar object called a blue straggler. These stars appear younger and bluer than their neighbors because the merger replenished their fuel supplies, giving them a second lease on stellar life. Collisions are more likely in environments where thousands of stars are packed into a volume only a few light years across. Over billions of years, the tightest stellar neighborhoods rearrange themselves through gravity and chance. In these crowded stellar cities, time moves differently, and space is never quite empty. The study of stellar collisions helps astronomers understand the dynamics of dense environments and the exotic objects that can form in them. Binary stars can be torn apart by tidal forces. Many stars live in pairs, orbiting each other in gravitational embrace, two suns bound together for billions of years. But even this bond can be broken. If a binary system passes close to the Milky Way's central black hole or through a dense star cluster, tidal forces can disrupt their orbit. The gravitational pull is stronger on the side closer to the massive object, creating a differential force that can rip the pair apart. One star may fall inward, captured or destroyed, while the other is flung outward, hurled into the dark at tremendous speed. In some cases, the ejected companion is accelerated to escape velocity, becoming a hypervelocity star speeding away from the galaxy. These stellar breakups happen silently in places we rarely see, a quiet tearing of ancient partnerships by gravity's indifferent hand. The study of disrupted binaries provides insights into the extreme gravitational environments near supermassive black holes and in the cores of dense clusters. Some stars escape the galaxy entirely. Most stars are gravitationally bound to the Milky Way, following orbits that keep them within the galactic disk or halo for their entire lifetimes. But occasionally, a star reaches escape velocity, typically over 500 kilometers per second, and is flung outward, never to return. These hypervelocity stars are rare but real. Some are thought to be ejected by interactions with the supermassive black hole at the galaxy's center, particularly when a binary pair wanders too close and one member is captured while the other is slingshot away. Others may be accelerated by three-body gravitational encounters in dense clusters or by supernova explosions in binary systems. Once free, they travel alone into intergalactic space, tiny lighthouses drifting far beyond the spiral's edge. They carry the galaxy's memory outward, becoming solitary pilgrims in the vast dark between galaxies. Studying these runaway stars helps astronomers understand the violent processes that can accelerate objects to such extreme velocities. The Milky Way contains stars from other galaxies. Not all stars within our galaxy were born here. Some originated in other galaxies, captured during mergers, or flung into our halo from distant regions of the local group. These intergalactic wanderers often move on unusual orbits, far from the disk, tracing paths that do not match the rotation of the Milky Way. They can be identified by their composition, which may reflect the chemical evolution of their original galaxy, or by their motion, which stands out against the background of native stars. Like cosmic immigrants, they bring stories from other environments, other histories, other skies. The Milky Way is not a sealed system. It is a living mosaic, slowly stitched together by time and motion, gathering stars from near and far into its vast structure. Each captured star adds to the chemical and dynamical diversity of the galaxy, enriching our understanding of how galaxies interact and evolve. Gas cycles between the disk and halo in a galactic fountain. Above and below the Milky Way's bright disk, gas rises and falls in a quiet loop known as the galactic fountain. Supernova explosions and stellar winds heat and eject material upward into the halo, where it cools, condenses, and eventually rains back down onto the disk over millions of years. This cycle stirs the interstellar medium, redistributes heavy elements created in stars, and helps regulate star formation by removing and returning gas on long timescales. It is a quiet respiration, a breathing motion of matter between the dense plane and the vast halo. The galaxy, in this way, does not just spin, it circulates, exhaling hot gas and inhaling cooled material in a continuous exchange that keeps its structure in motion across immense spans of time. This fountain process is essential for understanding the chemical evolution of the galaxy and the distribution of metals throughout the disk and halo. The galaxy's dust grains carry organic compounds. Within the clouds of interstellar dust that drift between stars, scientists have detected complex organic molecules, carbon-based compounds that form the raw ingredients for life. These include polycyclic aromatic hydrocarbons, simple sugars, amino acids, and alcohols. Though not alive, they are chemically rich, formed in the atmospheres of dying stars or within cold molecular clouds shaped by ultraviolet radiation. These tiny grains, carried across light years by galactic winds and the gentle push of starlight, settle into the gas that forms new stars and planets. Some may have fallen onto the early Earth, seeding our planet with organic compounds before life arose. The galaxy's dust is not just debris. It is a cargo of potential, drifting silently through the dark, waiting for the right conditions to participate in the chemistry of life. The discovery of these molecules in space has profound implications for the origin of life, suggesting that the building blocks of biology are common throughout the galaxy. Interstellar clouds may seed solar systems with ingredients for life. The birthplaces of stars are also the birthplaces of worlds. As planetary systems form from collapsing clouds of gas and dust, they inherit the chemical fingerprints of their parent nebula. If that cloud contains water vapor, carbon compounds, nitrogen, and other biologically important molecules, those ingredients may end up in comets, asteroids, or the atmospheres of newly formed planets. Some regions of the Milky Way are especially rich in such prebiotic chemistry, with molecular clouds full of complex organic compounds. We do not yet know how common life is in the galaxy, but the conditions for it seem to arise naturally and frequently. The seeds of life may be scattered far and wide, tucked into the galaxy's coldest cradles, waiting for a planet with the right conditions to nurture them into something extraordinary. This idea, called panspermia, suggests that life's ingredients, or even simple life forms, might spread through space on comets and meteorites, seeding multiple worlds with the potential for biology. Some stars rotate hundreds of times faster than the Sun. Most stars spin, but some spin incredibly fast, completing a full rotation in just a few hours, rather than the weeks it takes our Sun. These rapid rotators are often young, massive, and unstable, with equators that bulge outward from centrifugal force. A few reach such high speeds that they fling off material, forming glowing disks of gas around themselves. The Sun rotates once every 25 to 35 days, depending on latitude, a leisurely pace compared to these cosmic tops. But fast-spinning stars rotate hundreds of times more quickly, approaching the physical limits of how fast a star can spin without tearing itself apart. Their internal structures and evolutionary paths differ from slower stars. Their lives may be brief, but while they last, they spin like sirens in the dark, radiating energy and magnetic fields with unusual intensity. Rapid rotation affects everything about a star, from its shape and magnetic field to its stellar winds and eventual fate. The galaxy is tilted relative to the plane of the solar system. From Earth, the Milky Way arcs across the night sky in a graceful band of light, but it does not align with the plane traced by the Sun, Moon, and planets in our solar system. The galactic plane, the flat disk in which most of the galaxy's stars reside, is tilted about 60 degrees relative to the ecliptic, the path the planets follow. This tilt is why the Milky Way rises at an angle and shifts position with the seasons. We are part of the galaxy, but our own little system is angled slightly askew, a small tilted boat drifting through a larger spinning sea of stars. This misalignment is a reminder that the solar system's orientation was determined by the conditions in the molecular cloud where it formed, not by the galaxy's overall rotation. The tilt does not affect our motion through the galaxy, but it does shape how we see the Milky Way from Earth. Some stellar remnants are older than the galaxy's disk. Among the faint stars in the halo, astronomers have found white dwarfs, the cooling cores of once luminous stars, that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was still young, before its main structure had fully settled into the flat spiral we see today. Their existence hints at an earlier era of star formation, a deeper history etched into the outer halo before the disk coalesced. They have burned for billions of years, slowly fading from white to yellow to red, and eventually to black, carrying with them the quiet residue of a time when the galaxy was still gathering its shape. The disk may be bright and active, but the halo remembers further back, preserving relics from the galaxy's infancy. The farthest stars orbit well beyond the main structure. The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light-years from the center. These remote sentinels move through the galactic halo on slow, wide paths, taking billions of years to complete a single orbit. Many were likely captured from smaller galaxies in past mergers, now drifting in the outermost reaches like distant guardians. They are faint, sparse, and far between, but they help define the galaxy's true size, shape, and gravitational influence. The Milky Way is not just what we see in the bright disk. It extends deep into the dark, shaped by wanderers at its edge, stars so far from the center they barely feel the pull of the spiral's heart. These outlying stars are key to understanding the extent of the dark matter halo and the total mass of the galaxy. The Milky Way's shape is lopsided in several ways. Though often pictured as a symmetric spiral with evenly balanced arms, the Milky Way is subtly lopsided. One side of the disk is thicker than the other. The spiral arms are uneven in brightness and extent, with some more prominent and others fainter or fragmented. Even the stellar halo is slightly off-center, skewed by past mergers and ongoing interactions. These asymmetries likely arise from gravitational interactions with the Magellanic Clouds, with clumps of dark matter moving through the halo, or with the remnants of ancient collisions. The galaxy is not a perfect pinwheel. It is a living structure marked by tugs and twists, shaped by forces both internal and external. Its beauty lies in that irregularity, a graceful imbalance sculpted by billions of years of dynamic evolution. These asymmetries provide clues to the Milky Way's history and the forces that continue to shape it. Astronomers map the galaxy using variable stars. Certain stars pulse in brightness over regular intervals, expanding and contracting like slow, luminous heartbeats. These are variable stars, and some types, such as Cepheid variables and RR Lyrae stars, have well-known relationships between their brightness and their pulsation period. By measuring how long a star takes to brighten and dim, astronomers can determine its true luminosity, and by comparing that to how bright it appears from Earth, they can calculate its distance. These stars serve as cosmic yardsticks, helping us map the shape, structure, and scale of the Milky Way in 3 dimensions. They are living calibrators, blinking beacons scattered through the spiral that allow us to measure the vast distances and trace the architecture of our galaxy. Without variable stars, our understanding of the Milky Way's structure would be far less precise, and our maps far less detailed. The Gaia mission is revolutionizing our understanding of the Milky Way. Launched by the European Space Agency, the Gaia spacecraft is creating the most accurate 3-dimensional map of the Milky Way ever made. It has measured the positions, motions, and brightness of over 2 billion stars, revealing the galaxy's structure and dynamics with unprecedented detail. Gaia has uncovered streams from shredded galaxies, mapped the warp of the disk, traced stellar motions through time, and identified stars that were born together but have since scattered. With each new data release, Gaia deepens our understanding, turning a hazy smear of starlight into a sharp, living portrait of our galactic home. It is astronomy's most ambitious star chart, a quiet revolution unfolding among the stars, reshaping our view of where we are and how we got here. Gaia's data has already led to thousands of scientific papers and transformed nearly every area of galactic astronomy. The galactic plane marks a dense path of stars. If you look up on a dark night away from city lights, you may see a hazy river of starlight crossing the sky from horizon to horizon. That is the galactic plane, the thickest slice of the Milky Way's disk viewed edge-on. It is not a line, but a depth, a vast flattened band where the majority of the galaxy's stars reside. Through this plane, stars are densely packed, dust is layered, and star formation is common. From our vantage point inside the disk, we are looking along its length, peering through its richest corridors. This band is not just beautiful. It is the crowded, humming heart of where most stars live and die. The galactic plane is also where most of the Milky Way's gas and dust reside, making it the primary site of ongoing star formation and the birthplace of new planetary systems. The night sky is brightest toward the galactic center. The core of the Milky Way lies in the direction of the constellation Sagittarius, a rich, glowing concentration of stars, dust, and unseen mass. From Earth, we cannot see the very center in visible light, because thick clouds of dust obscure our view, blocking optical photons before they can reach us. But the region glows with brightness in infrared and radio wavelengths, which can penetrate the dust. Even with the naked eye, the area appears more crowded and luminous, filled with the overlapping light of billions of stars. We orbit far from this center, in a quiet suburb of the galactic disk, about halfway out from the core to the edge. But when we look inward, we glimpse the crowded city at the galaxy's heart, a dense, ancient region where stars are packed far more tightly than in our neighborhood. We see the Milky Way edge on from Earth. Because we live within the galaxy, We cannot look down on it from above and see its spiral structure as we might view another galaxy. Instead, we see it edge on, from the inside, as a flat ribbon of stars stretching across the sky. This edge-on view compresses the galaxy into a single arc, making it difficult to grasp its full three-dimensional structure from our perspective. It took centuries of observation, cataloging, and mathematical deduction to realize the true shape of the spiral we belong to. From Earth, we gaze through the disk, like standing in a forest and looking along the line of trees. We do not see the shape we are part of, only the vastness that surrounds us. This perspective has shaped humanity's understanding of the cosmos, making the discovery of the Milky Way's true nature one of the great achievements of astronomy. The galaxy holds far more than we can ever see. Even with our most sensitive instruments, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust, rendering entire regions invisible. Motion is hidden in silence as stars and gas move through space without fanfare. Dark matter outnumbers luminous stars by a vast margin, shaping the galaxy's structure without emitting a single photon. Between every star lies emptiness. Yet, within that emptiness lies potential, the raw material for future generations of suns and worlds. The Milky Way is not just what we observe, it is what we suspect, what we infer through gravity and mathematics, what we long to understand more deeply. It holds ancient light from the first stars, future stars not yet born, drifting worlds we will never visit, and questions still without answers. Within that vastness, somehow, we find ourselves. One planet among countless worlds, orbiting a quiet star in a spiral arm, floating through a story too wide for the eye to see, too deep for the mind to fully grasp. And yet, here we are, part of it all. And now, the stars begin to dim behind your thoughts. You have wandered through the Milky Way tonight, drifting from the supermassive black hole at its heart to the farthest stars in the halo. From newborn suns glowing in stellar nurseries to ancient white dwarfs cooling in the dark. From spiral arms shaped by density waves to the invisible scaffolding of dark matter holding everything in place. You have learned of collisions past and future, of rogue stars flung into the void, of gas cycling between disk and halo in a slow, patient breath. You have glimpsed the galaxy, not as a static photograph, but as a living, breathing structure, constantly evolving, constantly in motion, shaped by forces both visible and hidden. The Milky Way is vast beyond measure, containing hundreds of billions of stars, perhaps trillions of planets, and mysteries we are only beginning to unravel. But tonight, as you rest, know this: you are not separate from the galaxy. You are woven into its fabric. The iron in your blood was forged in the heart of a dying star. The calcium in your bones was scattered by a supernova billions of years ago. The oxygen you breathe was created by stellar fusion and carried across light years to become part of the cloud that formed our solar system. Every atom in your body has traveled through space, passed through multiple generations of stars, drifted in molecular clouds, and journeyed for eons before finding its place in you. You are made of stardust, quite literally. You are a temporary arrangement of matter that once existed in distant suns, recycled by the galaxy's endless processes of creation and destruction, brought together for a brief moment in time to experience the universe from a small blue world orbiting an ordinary star. As you close your eyes, the galaxy continues its slow turn. Stars are forming in cold molecular clouds. Supernovae are exploding. seeding space with heavy elements. Black holes are quietly accreting material. Spiral arms are sweeping through the disk, compressing gas and lighting up with young blue stars. Globular clusters orbit serenely in the halo. Streams of stars, torn from dwarf galaxies, continue their long, graceful arcs. Pulsars tick with metronomic precision. Neutrinos stream through everything, ghostly messengers from stellar cores. And somewhere, in a quiet spiral arm, about halfway out from the center, our sun carries its family of planets forward on a journey that has lasted billions of years and will continue for billions more. The universe is vast and ancient and beautiful, filled with wonders beyond imagining. But you do not need to understand it all tonight. You do not need to hold every fact in your mind or grasp the full scale of cosmic time and space. It is enough to know that you are here, part of this magnificent tapestry, connected to everything through the atoms you are made of and the light that reaches your eyes. It is enough to rest in the knowledge that the same forces that shaped galaxies and stars have also shaped you, and that the same matter that burns in distant suns flows through your veins. You have done enough for today. The questions can wait. The mysteries will still be there tomorrow. For now, let your thoughts drift like gas clouds in the galactic wind. Let your breathing slow like the patient rotation of the spiral arms. Let your body settle like dust falling gently toward a forming star. You are safe. You are held by the same gravity that holds galaxies together. You are part of something infinitely larger than yourself, and yet you are also perfectly, preciously you. The Milky Way will keep turning without you for a while. The stars will continue their ancient dance. The black hole will spin silently at the center. The universe will carry on its slow, majestic unfolding. And you, here and now, can simply rest. Close your eyes. Let go of the day. Let the cosmic perspective wash over you like starlight, soft and distant and beautiful. You are a child of the galaxy, made of its substance, shaped by its history, floating through its vast expanse on a world that circles a sun, that circles the galactic heart in an endless, elegant spiral. Dream of spiral arms and stellar nurseries. Dream of ancient stars and distant worlds. Dream of the quiet dark between the stars, where mysteries wait to be discovered. Dream of the light traveling across thousands of years to reach your eyes, carrying stories of places and times you will never visit, but can imagine, can wonder about, can hold in your mind as you drift towards sleep. You are exactly where you need to be, here, now, resting on this world, in this solar system, in this galaxy, in this universe. And that is enough. That is more than enough. That is everything. Good night, wanderer. Good night, stardust. Good night, child of the Milky Way. Rest well beneath the turning spiral. The cosmos holds you gently, and when you wake, the stars will still be there, waiting to tell you more of their infinite stories. Sleep now. Dream gently. You are home.